up, man?
Good morning.
Good morning.
How are you?
Good.
Good? Very good? Yes, good. So, hope you will be very good by the end of this class. Agree?
Yes.
Okay. If you are with me, so it's going to be a little bit tough topics, so please be with me. Okay, you can make it easy. So I don't know whether you had a chance to go through the syllabus, the schedule. There is a quiz coming up next Tuesday, quiz 1. Please notice there is a quiz, online quiz 1 on 30th January. Okay, quiz 1, chapters 1 to 3. Okay, come prepared for that one. And it is strictly in-class quiz. As I said in the first class, you must come here and take the quiz. Unlike you have a permission for accessibility, special accessibility. So, otherwise you must come here and take it. You cannot take it outside this room, okay, classroom. If you take it outside the classroom, you will get 0 points, okay. You cannot, but it's going to be online. You need to bring your gadget, whatever the phone or laptop or whatever, you can bring it here. And you are not allowed to go to any other website than Webcourses Canvas during this quiz time. Okay? It will be strictly monitored. So that's the reason why it is called a strictly in-class quiz. Yes?
How long will the quiz take? Just wondering.
15 minutes.
Okay.
You will get 15 questions and you have 15 minutes to answer them.
Okay, thank you.
Again, typically CA students answer within the first 5 minutes or so, but considering everyone, it's the 15 minutes. So, any other questions? And then, yes.
So because it's like 15 minutes.
15, 1 5.
Yeah, with 15 questions, is it more of like a definition?
Yeah, it's a multiple choice. It's a only multiple choice questions. There is not any, you don't need to solve any problems or anything like that. Not anything that requires so much time. That is for your exam.
Gotcha. Thank you.
It's just on chapters 1 to 3, correct?
Yes, including chapter 3 and including the topics I cover in the next class. Probably we will finish this chapter only by next class. So from 1, 2, and 3 is included. Yes?
Considering 90 like calculations, what would be like common sense?
Well, even if there are problems, it will be very, very simple ones. Any other questions? Okay. So, we are going to learn about crystallography, means the crystal structures, how atoms are arranged in metals. Again, why are we studying this? The crystal structure, arrangement of atoms with respect to aerospace materials. What is the relevance? Because you are studying the arrangement of atoms in the material. And your mechanical properties, especially we will come to slip and that type of properties, mechanical properties, slip of planes, slip of atoms, defects in the systems, defects in the materials, metals, alloys, and all those things. Then, there is a preference in which direction this defect propagates. That's based on the crystal structure. Okay, how many atoms, what is the density of your atoms in a given plane or in a given direction? How many atoms are there? So that's the importance of this study, okay? That's the reason why you need to know. That failure analysis is a very important part of aerospace and NASA, because typically I bring a NASA person here, the chief of material science in NASA, but I don't know whether this time we will get it or not, depending on her availability. But when she talks about these things, you can hear that, how important this failure analysis for NASA people is so important. Because whenever there is a failure, we need to learn from that failure, right? So you should not repeat it again. If the same failure happens again and again, what happens? You will be fired. Again, you will be fired for sure. You can afford the same mistake again and again. That's the reason why we are learning it. So you should be well aware of these things, what happens inside the material. Now, so what we have learned so far? We have learned about the crystal structure, cubic crystal structure. What are the different cubic crystal structures present? Face-centered, body-centered, simple cube. Simple cube is only one element, that is the polonium to simple cube. The other one is body-centered, and the third one is the face-centered. And beyond these cubic, the one other structure we are going to talk about is hexagonal HCP structure, hexagonal close packing. Okay, so that's the other structure we talk about. And what is the atomic packing factor? Look there. What is the atomic packing factor?
Volumes per volume of unit cell.
Exactly. That is the volume of the unit cell over the total volume of that unit cell. Number of volume of the atoms occupying that unit cell over the total volume of that unit cell. It's very simple. You can calculate it. So then we learned about atomic packing factor of SCC. Then let me ask you, how many atoms are how many atoms constitute a face-centered cubic structure? Do not look there. I don't know whether it's there or not, but how many? Completely inside a face-centered cubic structure. Someone from here? You need to remember, you can get these questions from your quiz. Means, what I meant is, you know that each corner is at the center of one atom, right? And that atom is shared by how many atoms in a cubic close packing? Come on, you should know these things right now. How many unit cells in one plane? 4. And how many unit cells in the on top of it? 4. How many then total? 8. How many corners are there? 8. 8 into 1 by 8? 1. Then what about for we were talking about face centered, right? And then how many face centers are there? 6. Each face centered atom is shared by 2 unit cells. So 3 plus 1 is equal to 4. These are important. Okay, what about BCC? How many atoms are there? How many atoms constitute a BCC structure? 2. Very good. You need to know these things. So, what about, the simple cube you already know. It's 1. It's 1. So that is important. So now, and what about the HCP? We looked at the HCP structure. What is the coordination number of HCP? 12. What is the coordination number of FCC? 12. And what is the packing factor of face-centered cubic structure? Packing factor. What is packing factor? face center cubic structure? Set. 0.74 or 74%. 0.74. What about BCC?
Down to 0.62. 6.68.
0.68. 0.68. Okay. And how many crystal systems are there total?
7.
7 crystal systems. Very good. And what about density? We know that mass by volume is the density. And we know mass of an atom. What is the mass of an atom? You don't need to even remember those equations. What is the mass of an atom? Atomic mass divided by atomic weight divided by Avogadro number. And if you know the number of atoms in a given crystal structure FCC, 4 into that atomic weight over Avogadro number, then there is a mass by volume. There is a volume there, V of that unit cell. V of the unit cell, if it is a cubic unit cell, it is a cube. So it's very simple, you know, N into atomic weight over V, volume of the unit cell, into Avogadro number. Avogadro number. Okay, so densities. So which one has the highest density among metals, metals, alloys, metals, non-metals or polymers and composites? Metals. And why?
Because of
The close packing. You see, because I told you so many questions even now. Okay? You need to be with me for all these things. You need to understand all these things. What is the difference between allotrope and polymorphism?
Allotropy is a special case of polymorphism that involves a single elemental solid.
And what you mean by that polymorphism?
That certain materials crystals can have more than one property. Structure.
More than one structure. Very good. More than one structure. That is called a poly. Poly means multiple. Morphism means structure. That is the polymorphism. So now coming to the crystal structure. Okay. Now we need to go back to our concept. You know, if you need to imagine this room as a cubic cube or a cube-like structure. Okay, unfortunately it's not cube-like structure, but just imagine it is a cube-like structure. And what is our concept? That side is origin, and that is
The x-axis,
x-axis, and this is
y-axis,
and this is.
z-axis.
And what about that direction?
That was minus x,
Minus x,
minus y,
minus y,
and minus z.
minus c. Very good. Now, you want to, this is a cube, and you want to look at the point. You know, if you have a point, for example, if you are sitting somewhere there or somewhere here, you need to locate that point. Okay, you need to locate that point. One, that is the point coordinates. Second one, direction. How we write the directions for such a cube. Okay, why cube? Unit cell. Remember, cube, we consider it as a cube basically because it's a unit cell. And unit cell we talk about, at least for the first two, is the close packing, BCC, FCC, and such things. They are exactly like a cube. And then second one is the direction, and third one is the plane. Okay, how we can write the coordinates of points, direction, and plane. That's what we are going to talk about now. So, if you consider a person somewhere here, we locate a person somewhere here? Think about it. We know, and also remember the x-axis we consider it as A, y-axis B, lowercase a, lowercase b, and lowercase c. Are you with me? So now tell me the position of a person somewhere at the middle, along this direction, not anywhere in the space, but somewhere here. How can you locate that person with respect to coordinates? That is, point, this is a point, P of x, y, and c, px, py, and pc. That's what we are going to try. Okay, your px, py, and pc. How can we do that? That's what we are going to do now. I will write that one. So this is the px, py, and pc. Let's first write and indices or point indices. Q, R, and S. Q, R, and S. These are the point indices. And now we can write this P, X. Okay, any point. We are writing any point within this unit cell, but I talked about a point somewhere there at the middle. And we can talk about that one later. But what? The px can be written as q of a, py is equal to r of b, and pc is equal to s of c. Q of a, r of b, and S of c. These are the steps we need to follow to write this one. The point coordinates lattice position px, py, and pc. So this is the fractional multiple of this is written in the form of the fractional, you can write it in terms of the fractional multiples of a, b, and c. And the integer multiple of the lattice constant, you can just convert it into the full number by multiplying it with certain other factors. I am going to show you that one. First, let's write this one. We are taking, unless I told you about that the surface, but let's take a point at the center of this cube. Okay, at the center of the cube. Imagine a point somewhere at the center, somewhere in space, somewhere here. Okay, that point we are going to consider. So how can we write that point coordinates? Px is equal to q of a. Okay, px is equal to q of a is equal to. Now you need to make use of your thinking machine. You have that corner. We can talk about that point in terms of the x-axis. The total length is a, and how much is going to be the length up to the center of this room if it is a cube.
It'll be some multiple of a.
Multiple of a, which is, so if it is exactly at the center, what is going to be that multiple?
It is going to be 1/2 a. Wait.
Half of a, absolutely. Half of a. Half of a. And P of y is equal to R of b, which is equal to
1/2 b.
1/2 b. And P of c is equal to S over S into C is equal to
1/2 C.
1/2 C. Yes,
Could you explain the AR and S? What are those?
just Q, R and S, right?
Yeah, QR.
Q, R and S, they are just indices. Now, he said that, or you guys said that this is half A. The Q is 1/2.
So it's just the.
That is the indices, just that distance with respect to A. That's it. So if it is somewhere here, it's not going to be half, but it is less than that from the origin, right? Maybe 1/3. Then 1/3 of A. Okay? And what about B? It's going to be 2/3 of B. And the C, if it is somewhere here, maybe it's 1/3 of C. That's it.
Yeah, Q, R, and S are multiples of A, B, and C respectively.
Yes.
So are they like scalars?
Actually,
Are they scalars or just constants?
no, it varies. They are variables depending on the position, location. So it is going to be half if it is there, and if it is 1/3 somewhere here. Okay. So, but A is a constant. A is for a given unit cell. It is a constant. Means it is fixed value, right? So that is the A, B, and C. Now, solve it in terms of Q, R, and S. So, what is going to be the Q? Q is equal to so what is going to be your coordinates? Half, half, half. Any questions? Any question, anyone? Yes.
For this coordinate system that we're gonna be using itself, it's always gonna be based on having a value of 1 at the most edge of the unit cell.
Yes.
So we're gonna
Yes.
be-
So this unit cell
So regardless if it were a rectangular system per se.
is a cubic. So always cubic, right?
Oh, it's always gonna be-
It's a face-centered cubic or body-centered cubic. In hexagon, we are going to see later. Okay, so only for HCP, sorry, it's only for body-centered BCC and FCC. Okay? And now you can determine, if you know the indices, you can determine that point coordinates for any system. So it's not at all a big deal, I assume. Once you know what is the parameter there, coordinates where you can locate it 1/3 of A, 2/3 of A, or 0.2 of A, 0.5 of A, 0.75 of A, like that one. You understand it, right? And that is the point coordinates. Now if we can go to the next one, crystallographic directions. Okay, let me say the steps involved. Again, X, Y, and Z directions. X-axis, Y-axis, and the Z-axis. And you have a direction, it's a vector, and assume that this is a direction. Okay, like this one going, this is going through that cube. Remember that. Assume that this direction is going through that one, going in this direction, or whatever direction. It can go in this direction, it can go in this direction, it can go in this direction, whatever direction. We are trying to determine that one. So, first you need to consider if this is the one, it starts from somewhere here. This is the point, the first point, point 1, x1, y1 and c1. And this is that, the head, the tail is x1, y1 and c1. And the head is x2, y2 and c2. Got it? Point 1 is x1, y1 and c1. Point 2 is x2, y2 and c2. So, now look at this one. Okay, let's write the steps in bold. First one, you have to consider the right-handed x, y and c coordinates, or x, y and c system should be constructed. And second, determine the tail points one, that is, this is the tail point. Okay, this is the tail point, that is x1, y1 and c1, x1, y1 and c1.
What did you write on the first step?
So that right hand system, our x, y and c.
He just wrote right-handed XYZ system, indicating that it needs
So
to
I-
be determined.
It's okay, so that is the x, y and c system, okay, that is that right-handed system. So determine tail point, that is x1, y1 and c1. Then what is the next one? Point 2. What is the point 2? This is the point 2. x2, y2 and c2. Now, third step is subtract the tail coordinates, subtract tail coordinates from the head coordinate. So then normalize it with the lattice parameters A, B and C. Which is x2 minus x1 over A, y2 minus y1 over B, and z2 minus c1 over C. So, 5 adjust to the smallest integer. Okay, adjust to the smallest integers and enclose in square bracket. Got it? Yes.
What does 5 say? Adjust the smallest.
Adjust to the smallest integer value. You will see it now. We are going to see a few problems. So now, look at this one. This is the point. Okay, where is your origin? Your origin is here. And it is going like this. Okay? this vector is going in this direction like this. Are you getting it? So, you know, and this is from the point, the origin, to this side. You see, it meets this side here. Now, what is x1, y1 and c1? It's the origin 0, 0, 0. And what is x2, y2 and c2? Tell me, what is x2, y2 and c2?
x2 is equal to a.
Yeah, someone else. y2, 0 and c2? Yes, 0, 2. Half of c. Okay, got it? Any question, anyone? You can ask me. There is, you can ask me right now. There is absolutely no problem for that one. Yes.
You just assume that's half of.
Yeah, that will be given. Don't worry about it. Whether it's half or 1/3 or 3/4 or whatever, that dimension that will be given there. So, any question now? Okay. So, x2 is equal to a because it is going in the x-axis, a distance. There is no component in the y-axis direction because it's not traveling in the y direction. And if it is half, this is 1/2 of this side, and therefore C2 is equal to half. Then what is the fourth step? So x2 minus x1, that is a minus 0 over a, and 0 minus 0 over b, and c half minus 0 over c. So this is going to be 1, 0, half. Now convert this into, this is 1, 0, half. And you need to convert it into an integer. What do you need to do in that case? Multiply by 2. 2, 0, 1. And then what you need to do? Square bracket. It's so important. If you do not put square bracket, you will lose points. Because you can half these numbers for whatever, for direction or plane. So that means that it's not sure whether this is a plane or a direction. So that's the reason why it should be in a square bracket. No, there's no commas here. Okay, now let's look at this one. Again, you need to have this in mind. What is the direction? This is the direction. This is the origin. And as I said before, you have these cubes arranged in this given plane on top, bottom, and so on. So this is from that origin to where? From that origin into the other room, next room, to that corner over there. That is the direction. Did you get it? So that is the direction going from the origin to this. This is the unit cell behind. So that's where it is going right now. So you need to tell me what are the directions x1, y1, and c1. What is x1? 0. x1 0, y1 0, and c1 is equal to 0. And then what is the point 2? This is the point 1. Point 2 is equal to x1 is equal to negative a. So y x2, this is x2, y2 is equal to b. Very good. B. And what about C2 is equal to
C.
C. See, any question? Any question you can ask me. Don't be ashamed, there is nothing like that one in this class. Okay, I hope you all got it. So now what we need to do, x2 minus x1, that is minus a minus 0 over a. So what about this one? B minus 0 over B, C minus 0 over C. So this is going to be minus 1, 1, 1. So minus 1, 1, 1, and finally you don't need to do any reduction or normalization because already 1, 1, 1, so it should be minus 1, 1, 1. So this minus 1, you need to put it, please note here, this minus 1 should be, put it as a over bar. Okay, when you write the direction, the minus 1 should be represented as an over bar. So this is an over bar. So now you can see that all the equivalent directions UVW, like 1, 0, 0, 1, 0, 0, so equivalent directions are represented by this one here, UVW. Okay, whenever you see something like this, this is 1, 0, 0. This is represented by this brackets. When you see it, that means they are equivalent directions. Equivalent directions. And look at this one: 1, 0, 0. Minus 1, 0, 0, 0, 1, 0, anything with the minus or plus 1 with the two zeros. They are equivalent directions. Okay, equivalent directions. Now, why we are saying it, equivalent directions? You are going to see it in the next page too. Why? Because think about it, they are unit cell, they are all same, right? It's the same structure repeating over and over again. So whatever this direction is going to be equivalent with respect to a given unit cell, maybe it's going to be different, but in that case it is going to be minus 1 is going to be plus 1. Got it? So that's the reason why we say that they are all equivalent directions. On minus 1, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, and so on. All these are equivalent directions. Now, let's do another problem. What about this one? Okay, so point 1. What is x1? X1 is A. Very good. Very good. What about x2? Sorry, y2? Sorry, y1. Y1? Very good. 1/2 B. What about C1?
0, 0.
So point 2. X1?
Minus A.
Very good. Minus A. And y2 is equal to
B.
and C2 is equal to
C.
C. Now, x2 minus x1,
Two.
x2 minus x1 is minus a over a.
Negative two.
That is 2. Okay, we will come to that one. So y2 b minus half b over b. And what about c? C is equal to c minus 0 over c. So this is going to be minus 2 minus 2 half. I got 1, that's the result. Half and 1. Then your conversion minus 4, 1, 2. And therefore this should be written as 4 over bar 1, 2. Again, if you did not follow it, ask me right now. The reason why I am asking is it will be beneficial for others too. So if you do not follow it, please ask me. Now, HCP structure. So, there is a video I will show you, but you know, when you have a HTTP structure, hexagonal closed pattern structure, you know, your axis, 3-axis system is similar to that X, Y, and Z, but it is like A1, A2, and C coordinates. Okay, this is A1. You can see a video, then you will get a better idea about it, but for the time being, just look at it. Here, this is the origin. Okay, this is the origin. And you remember I told you that HCP, hexagonal closed packing, HCP, hexagonal, this is made up of how many parallel fibers? 3. And what are the 3 parallel fibers? If you look at this one, this is 1. For example, this is the second one, and this is the third one. Got it? We can consider it as a combination of 3 parallel fibers. The advantage is that now look at this one. You know, you see this is the A1 axis, again one going towards you. That is that A1 axis, and the other one going in this direction, that is A2 axis, and this is the C axis itself. Okay, you have a question? Yes. This is A1, A2, because to avoid that confusion for the cubic system and hexagonal system, that's the reason why it is called A1, and this is A2, and this is the C axis. And you can see that this A is equal to this, the distance from here to here is equal to the distance from here to here. So we can take it as A itself, 1A itself, this distance as well as this distance. But you can see the C is different, right? C is different. This is longer than the typical one. So C is different in this case, but this is the 3-axis A1, A2, C coordinates. Got it? Now, in certain, for more complex systems for HCP structure, for the directions and the planes, it is harder to distinguish between the symmetries. It is harder to distinguish between the symmetries. Therefore, there is another system called a 4-axis system. Okay, the 4-axis system is like, this is the A1 direction, this is the A2 direction, and this is the A3 direction, and this is the C direction itself. Got it? There is a 4th axis here, but you don't need to worry about that this axis right now. Basically, how to calculate it from here. Actually, this can be calculated from this one itself, from the structure itself, by dividing it into different structure grids and all those things. But you don't need to worry about that right now. What we are going to do is we determine the 3-axis system and just convert the 3-axis system into a 4-axis system. Got it? The 3-axis system, we first determine the indices for the 3-axis system, coordinates for the 3-axis system, and that 3-axis system will be converted to a 4-axis system. That's the strategy we are going to follow. Got it? Okay. Let's watch this video how these parallelepipeds are. Then
when you get your next big idea, say smartly ketchup.
this is the one parallelepiped. Again, we are talking about one of the 3 parallelepipeds. Then you're joining 2 other parallelepiped with that one. Now look at this one. This is the structure of that external closed vacuum. And you can see the atoms at the corners. And these are all the corner atoms. These are the other 3 atoms which are completely inside that hexagon. And this is the face-centered atom, and there is another face-centered atom at the bottom. This is the structure. So I think that is basically it. And you can see when you add more and more HCP structure, how the crystal, the whole crystal looks like. That's what they are showing right now. How that whole crystal is made. That's it. You see how beautifully the structures are made by the nature, right? How well arranged and well optimized all those things. So basically, coming from the quantum mechanics, from the atoms and to the electrons and to the atoms, and then building of the atoms together and to that crystal structure and all, right? It's beautiful how they are arranged and they are made into a crystal itself. So now let's see how we can determine the different directions. So these steps are more or less the same. Yes.
Yeah,
Thank you.
you're welcome.
So again, the steps are more or less similar. What do we need to do? Tail and head. Point 1 and point 2. X1, like X1, Y1 and C1. It's 1, y1 and c1. Point 2 is x2, y2 and c2. Okay, so this is like so this is, if you with respect to this one, it is a1, a2 and z1, and here also the x1 of the a1, that is going to be the next one. The since it is a1 and a2, it may be a little bit confusing, so better let's consider this x, y and z, but we can take this a. You remember this x is in this direction a1, y is in the direction, this one is the a2, and you can say that this length is a, this length is a, and this length is c. Okay, so now similar to the other one, what we need to do, the second, this is the first step, step 1, step 2. Again, what is step 2? x2 minus x1 over a, y2 minus y1 over a, and c2 minus c1 over c. Then adjust to the smallest integer, step 3. Step 4, enclose in square bracket. Okay, and remember in this case it is called u v w. So this is equal to u is equal to x2 minus x1 over a, v is equal to y2 minus y1 over a, and w is z2 minus z1 over c. Now the step 5, convert, this is the 3-axis system. Step 5 is to convert 3-axis system to 4-axis system. And how can we do that? This can be, what is the 4-axis system? 4-axis system is represented as uv, lowercase u, lowercase v, and there is a t and w, u, v, t, w. So now how can you convert this uppercase, that 3-axis system, into a 4-axis system? Here is the equation, u is equal to 1/3 of 2u minus v. V is equal to, lowercase v is equal to 1/3 to v minus u. Okay, these are all uppercase. Okay, this is uppercase v, this is uppercase u. And t is equal to minus of lowercase u plus lowercase v.
Could you speak the zebra up a little bit? Thank you.
T is equal to minus of lowercase u plus lowercase v, and W is equal to the W you got here itself, the W you got here. The lowercase w is equal to uppercase W. So you will be asked the question, find the indices and convert it to 4-axis system. So the question. You will be given a direction and you will be asked to determine this 4-axis coordinates.
Is the lowercase u equals 1/3? 2 times lowercase u or high case?
Lowercase. Please remember this is lowercase.
Yeah, the other ones inside, they're all uppercase.
These are all uppercase. Okay, so remember this. What you get from 3-axis system is the uppercase U, V, and W. What you get from the 4-axis system is lowercase U, V, T, and W. Yes.
T is equal to lowercase u plus v?
Exactly. Minus of lowercase u plus lowercase v. Okay, let's do some problems from here. So now determine this direction, this green arrow. You can see it, right?
Yeah.
So this green arrow here. So what is that x1, y1 tail location? Tail location in terms of, we can write it A1, A2, and the C axis. What is the tail location?
0, 0, 0.
And the head location? Head location?
A0.
Very good. Did you get it? Everyone? You need to think about it. If you don't follow it, if you don't understand it, please ask me. I can tell you, but I want you to think first. Are you getting it? So you can see, if you look at this one, how much it is traveling. This is the parallel paper. In this A1 direction, it is traveling this much, right? Agree?
Yes.
And in the A2 direction, this is, what is this? This is A. And in the A2 direction, again, this is A. Therefore, your coordinates will be, tail coordinates are 0, 0, 0. This is, head coordinates are A for the A1, A for A2, and for C it is 0.
So in this case, A, generally speaking, can indicate the distance from the center of the crystal to the edge, or the distance from the center of that unit cell to the edge, or corner.
Yeah, but this is the representation, how you can reach there. So for example, as I said in the previous case, the cubic structure. So how can we think about it? How can I reach somewhere there? It's just like that one. I need to, just for the representation sake, we can directly walk from there to here. I agree. But how can you represent it? You can represent it only in terms of that coordinates, x, y, and z coordinates. That's the reason why it says that you need to go halfway through the x-axis, then halfway through the y-axis. Okay, since we are representing in x, y, and z, the same way this one too. In the A1 direction, you need to walk this much, and A through direction, you need to walk that much. That's how you can reach that point. There is no C component in that case.
Okay.
Because we are not C component for any C component, either you should go in this direction or in that direction. So now you can easily do it. Normalize the difference is, you know, it is very easy now. A minus 0 by A, this is going to be 1, 1 and 0. You know how to solve it, right? And since we don't have that much time, I'm just writing 1, 1, 0. Reduction is also the same thing. 1, 1, 0. And the brackets, it is 1, 1, 0. Now you need to convert it to the 4-axis system. Fifth system, converting it to 4-axis system. How can you do that? So U is equal to, what is a 4-axis system? Remember, it is lowercase u, lowercase u, lowercase v, p, w. So u, lowercase u is equal to 1/3 of 2u. 2u is equal to 1. 1/3 of 2u minus v. V, what is v?
V is 1.
1. This is minus of. This is not.
The only negative I noticed for the coordinates is when applying t, because u is positive 1/3.
Yeah. So I'm just writing it 1/3. There is no minus here. This is 1/3 of 2 into 1 minus 1.
Okay.
This is again 1/3 of 2 into minus 1. And t is, this is equal to,
That is minus the quantity u plus v, lowercase u plus lowercase v.
yeah, so what is the value there? This is 1/3, this is equal to 1/3, right? This is minus of 1/3 plus u plus v is equal to minus 2/3. So w is equal to 0. So what is the answer? So this is where you need to convert it. So you need to multiply it by 3. By multiplying it with 3, what you get is 1, 1 minus 2, 0. Therefore the answer is 1, 1 minus 2, 0. Yes?
If we're four-dimensional, is it too broad or is it
Oh, again, that's true. That's correct. It should be over bar. Okay? It should be over bar. Thank you. This is not, you should represent it as an over bar. Like 1, 1 over bar, 0. If I will solve more of these things if I get time in the next class. So let's move on to the next one, the planes. Now this is easy if you understand it. So far so good. Is there any question? Is there any question so far? Okay, Now it's going to be able to consider planes. So this is our cube. Okay. So the crystallographic planes. What is the crystallographic planes? You have this cube and whatever plane you have here. For example, this is one plane. Agree? This is another plane. This is another plane, whatever the plane, there can be plane in between this, which is going through this one, through here, or whatever. So, that's what we are going to consider, the crystallographic planes, and it is represented by three Miller indices. It is called the Miller indices, H, K, and L, and it is represented by parentheses. Parentheses, planes are represented by parentheses, and the indices are H, K, L. Got it? So, what is Miller indices? Miller indices are the reciprocals of three axial intercepts intercepts for a plane cleared of all the fractions and the common multiples. What does that mean? It is the reciprocal. Reciprocal is nothing but 1 pi, right? It is the reciprocal of the axial intercepts for a plane cleared of fractions and common multiples. Now, if there is a plane like this one, okay, if there is a plane like this one, so what is the intercept of this plane with respect to x-axis? Intercepts at A. Intercepts at A. Did you get it? This is the origin, and this is the plane, and this plane intercepts at A. Agree? If it is, and what is the intercept for the y-axis for this plane? So it runs parallel to that one. Agree? It runs parallel to that one, that y-axis. What about the z-axis? So we can say that this intercepts this y-axis at infinity. Agree? At infinity. And what about this one for the z-axis? Again, it runs parallel to the z-axis. So it intercepts only at infinity. Got it? And what about this plane? What is the component for the x-axis? Infinity. You always remember, we are just taking this intercepts. What is actually the Miller indices? Miller indices is the reciprocal. Okay, reciprocal of this one. So for this axis, we are just considering the indices. So for this one, for the x-axis, it is infinity. Y-axis, B. Y-axis is B, right? The origin always comes to this origin. Here, this is the origin, so B. And what about for the z-axis?
Infinity.
Infinity. And what about this plane on top?
X index is infinity.
X is infinity, Y infinity, and C is equal to C. Clear so far? Okay. We consider only these planes which are intersecting at these two axes right now. So, but these are the rules. Steps. So all parallel planes have identical Miller indices. They are all equivalent planes. I will come back to that one, or I can say that one. This is the meaning. All parallel planes have identical Miller indices. which means that if this is the plane passing in like this one here, or like this here, or like this here, or like this one here, they are all equivalent planes. Okay, they are all equivalent planes. Did you get it? Whatever this one, these are all equivalent planes, right? Even if it goes through this one, it's going to be half, but you will see that we will multiply it with that, make it into, reduce it to smaller integer and so on. These are the steps. So if the plane passes through a selected origin, now what happens to this one? The first one is that the plane, listen here, if your plane passes through the origin, okay, for example, this plane passes through the origin now. Agree? So what happens in that case? The rule step says that if your plane passes through like this one or like this one or whatever through that origin, you need to move the origin to the neighboring unit cell, nearby unit cell. Or you need to find an equivalent plane. Okay, you get it? So if it passes through that origin, you need to find that indices with respect to a neighboring unit cell. The next one over here, you need to consider that as the origin and then get the indices values for that way. That's the meaning. So if plane passes through the selected origin, either another parallel plane must be constructed or a new origin must be established at the corner of a unit cell. And crystallographic plane either intersects or parallel each of the three axes, length of the planar intercept for the each axis, A, B, and C for X, Y, and C axis. So here we represent it as the intercepts, okay, are represented as planar intercepts are represented as A, B, and C. And now you take reciprocals, that is 1 by A, 1 by B, 1 by C. Okay, and then reciprocals are normalized in terms of their respective A, B, and C lattice parameters. That is, what is the lattice parameter? It is A over A, B over B, and C over C. And then reduced to the smallest integer value and enclosed it in parentheses, there is no commas, just HKL values. And this is called the Miller indices. Whenever you hear Miller indices, that means they are the indices of planes. Okay, they are the indices for planes. So in summary, it's HKL value. You can write it as n. N is that common factor. N into A by A. K is equal to n into B by B, and L is equal to n into C by C. Then n is just a factor required to reduce the HKL value to integers. These are the steps involved. Yes.
So if there don't intersect, you need to take a corner of a different unit cell to be able to get that intersection? Is that?
No. If it passes, only if the plane passes through your origin. Okay? Only if it passes through the origin. Otherwise, you should not take it like that. As I said, in the case here, this is the origin, right? And if the plane is passing through that origin, we cannot take that intercepts. In that case, we need to move it. Very good. So, now this is going to be very easy for you if you understood the whole thing. Example here in this case, you need to write one intercepts. What are the intercepts for this one? A, B, and C. Tell me, what are the intercepts? A
One.
is 1, B is equal to 1, and C is?
One. No, zero.
So then reciprocal? Then which is equal to reduction 1 over infinity 0, and then Miller indices is 1 1 0. You need to show all these things if such a question is asked. You need to show all the steps. Please remember that for your homeworks and exam. You need to show these steps. Do not just show the final answer. You will not get 2 points if you just write the final answer. And what about this one? Intercepts? It is half, 1/2, and B infinity, and C infinity. So reciprocal. So it is 2 1 1. Sorry, 2 0 0. 2 0 0. So Miller indices is so I know I will finish it in 2 or 3 minutes, okay? So crystallography plates, yes. Sure. So crystallographic planes. Now you already know what are these things. The indices, right? These are all indices. What we are talking about. When it is here, it is 0 0 0 0 1. These are all equivalent planes. 0 0 1 0 0 1. What about this one? It is 1 1 0. 1 1 0. These are all equivalent planes. And what about this one?
1 1 1.
1 1 1. Very good. And also remember this one. In the future, it will be, you may need this one. This a unique character of cubic crystals is that planes and directions have the same indices are perpendicular to one another. Hold on for a second. You need to remember for future problems this one. For a given cubic crystals, your planes and directions having the same indices are perpendicular to each other. Okay? Then this is true only for cubic unit cells. Okay, thank you.